Today's seminar, the speaker of today is Grasiane Luz. She just finished the master's degree in the University of Sao Paulo and just defended the last month the thesis for the master's. And she has been working in geomagnetism and oceanography, and this has some relation with things that we work here, that is cosmic magnetic fields and dynamo theory. This is not properly speaking the topic of Grasiane's research, but is related to measurements of magnetic fields. So Axel gave me this is a table of reversals, but probably Grasiane will tell a little bit about this in the talk. Okay, so Grasiane.
Okay, good afternoon. I would like to thank you for the opportunity to show you my results, and I'd like to encourage you to ask me questions when you want, because it's the first time that I'm presenting something in English, so probably I will not be clear in some points of the presentation. And I will present you a little about the work that I made during my master's degree in the Institute of Astronomy and Geophysics of São Paulo University, under the supervision of Ricardo Trindade. During these 2 years, I made environmental magnetism using marine sediments with two proposals: obtain geomagnetic data from Earth geomagnetic data, and to do paleoceanographic reconstructions in the South Atlantic Ocean. Only for this was the first chart with inclinations that have been done in the Earth. It was done in 17 something, and for a researcher in the University of Stockholm. So, before I show you my results, I will briefly tell you a little about how is the Earth magnetic field generated. This figure is showing the inner structure of Earth. Here the crust, the mantle, and here the outer liquid core and the inner solid core. So the magnetic field of Earth is generated in this metallic layer that is represented here. Is a dynamo process doing convection motions and doing Earth rotation. I'm not going to deep in this subject because I know that you know much more than me about dynamo theory. So I will speak a little more the behavior of magnetic field at the surface of the Earth. So to understand the behavior of magnetic field in the past, we need to know what forms does the field take in the Earth's surface. So we need to imagine that in the center of Earth we have a bar magnet that's pointing southward, and it generates this magnetic flux line that leaves the South Pole and enter again in the north. But we know, using a mathematical model that is called the geocentric axial dipole, that this dipole is not aligned with the Earth rotation. So we know that there is an angle. We know that this geomagnetic North Pole that's generated by this model is tilted in relation to this North geographic pole. This angle is the declination, and is one of the components that we need to understand the behavior of magnetic field in the past. Now, in the present magnetic field, you know that it's about 11 degrees, this angle. Another component that we need to obtain is the inclination of magnetic field that is represented in this figure. This inclination is the angle between the total intensity of the field and its horizontal component. And we know that the inclination is not the same around the world. It varies from 0 at the equator to plus 90 degrees and to minus 90 degrees southward. another important aspect about the morphology of magnetic field is that the geomagnetic pole. No, I told it. Okay. That this geomagnetic pole is not located in the 90 degrees inclination. So there is a difference between the inclination in Earth magnetic pole, the real magnetic pole that we measure at the surface, and this mathematical pole. What means that this magnetic field of Earth is not totally dipolar. This field has some non-dipolar components. And with these components of field, we can do some charts like this one that shows the variation of the features of field in the surface. In this case, this was the first chart of declination, and this red line is showing the 0 degree declination at the surface of Earth. And when we compare this chart that was done in 70s and 80th century, we can see that the 0 declination line is not above the Atlantic Ocean anymore. It drifts westward. So we can see that the features of magnetic field are changing with time. And it's better represented in this figure, where we can, it represents the last 4 centuries of variation in declination of the field. And we can see the 0 degree line drifting from east position to a westward position. And besides this drift in directional, sorry.
Is it data from observation or this?
Yeah, I'm sorry, I forgot to mention. This model have been done based in observatory that are direction measurements, and navigation, and archimagnetic data. Because the observatory data covers only the last 200 years ago.
So this is all from observation, this is not a simulation?
No, simulation no. Everything is observation.
Mm-hmm. That's the surface of the Earth.
At the surface.
So these are the 2 poles that you now see are the ones that you showed earlier.
Yeah, these are the North Pole and South Pole.
And they disagree slightly with the what you call geomagnetic pole, which is then a fit to a dipole.
No.
It's not.
The geomagnetic pole that is generated by a model doesn't fit with this pole that we measure.
Yes, that's what you showed in the previous.
Yeah, I forgot to mention that it's possible to see here that the pole is not fixed.
Yes.
It changes with time.
And this model, how many multipoles does that take into account?
How many what?
Multipoles, or is it just a dipole?
Non-dipolar components. How many?
This is what you call GAD. This type, the GAD, which you plot the axis.
The geomagnetic pole?
Yes.
So, again, what's the question?
So the question was, in this GAD, of which you showed the axis in this previous plot, how many multipoles does that take into account? Is it just the first one, the dipole?
Only dipole
Only
components.
Dipole,
It doesn't have the non-dipolar components.
There are some beautiful reconnection events in that.
These changes in the features of magnetic field can be observed in the intensity of the field as well. So in this figure we can see the high intensity in the poles, and a region with low intensity here that is called the South Atlantic magnetic anomaly. I forgot to mention that the intensity changes with latitude, how you can see from the equator to the pole, increasing this to the poles, increasing this intensity.
So these, it's quite amazing that you have over Siberia also this maximum, because inclination there was nothing near 90 degrees, right? In Siberia, where you see this, these 60 micro-Tesla contours, the inclination was not particularly high, was it?
No, but no, because the inclination inclination in when we measure is not 90 degrees because it has the non-dipolar components. It's not only the dipolar.
But over Alaska, of course, Canada degrees roughly. That was close to 90 degrees.
61 instead of
Sure, but there's another 60.
No.
Okay.
It doesn't shows only the dipolar components.
Over how many years is this movie?
The last 200 years, because these were made only using observatory direct measurements, not navigation or archaeomagnetic material.
It's interesting to note that the time constant of the Sardinian variations is shorter than of most of the others.
3 cycles in 200 years.
So this map is showing the distribution of these observatories that generate the data for constructing that kind of charts. And the measurement of intensity was possible only when Gauss invented this method for acquiring the intense magnetic field. But these measurements are really precise, but it covers a small part of a small period of time, only the last 200 years ago. So to study all this part of field, we need to use another techniques. For example, use archaeomagnetic material that are collected in archaeological sites, ceramics. So here I'm using an example of a work that has been done for a PhD student that is working in the same group that me. And he collected these samples in Bahia, in the state of Brazil. And when he compared his data with the models for this region, we see that for some periods and with some models, it fits in a good way. But some data doesn't fit very well. It can be due or because there are big errors with the samples, or because these models don't represent the real variation of magnetic field in this region. Because these models are constructed using the existing data in a region, and we don't have a lot of data in South America. So probably this data is a good record of magnetic field, and the variation of the models don't show local features of the field. But the archaeomagnetic ceramics only permit us to study even using these ceramics, we can study still a small part of the time. We studied the last 500 years. So to understand the field, for example, million years ago, we need to use geological material. Here, I'm using an example of a record obtained from marine sediments collected in South Atlantic. And the graph is showing the variation of intensity during the 800,000 years, the last 8,000 years. So how you can see, there are some decrease in the intensity of magnetic field, and we know that this behavior can be associated with changes in the direction of the field. So in this figure, what we can see is that this decrease in intensity are the excursions of the direction in the field. Excursions are changes in polarity, but not a reversal. So the pole drop, change the moves the direction more than 45 degrees, but not reverts totally, so back to the original pole. But here in this figure we can see also the last reversal that occurred in magnetic field, that is the Bruins-Matuyama boundary. This Bruins is the present-day crown. It has normal polarity, and Matuyama and Gilbert has the reversal polarity. This table is showing the four reversals that happened in the last 5 million years. And when we stood short period of time, short in geological times, I mean 5 million years, we can maybe to average a frequency for these reversals. But when we stood a large period of time, like here, 160 million years ago, we can see that this frequency is not the same in some periods, and in a particular period, we don't have any reversal. This period between 80 and 120 million years ago is called the supercrown of Cretaceous, and we don't see any reversal, and we don't know why during this huge period it didn't happen.
So the last reversal you said was the one to the right at 800.
Yeah, almost 800,
8
million
years ago. But what is actually a VADM?
VADM is virtual axial dipole moment.
Yes.
It's an approximation that we used to do to compare intensity of magnetic field in different regions of globe. Because if we use microtemperature intensity, we cannot compare because it changes.
Yes. So the actual reversal one doesn't really see, but it's probably compatible with the fact that the overall magnetic field of this VADM becomes very small.
I didn't understand, sorry.
Of course, I mean, one cannot from this plot see whether or not you had a reversal, because you only see the overall field strength somehow.
No, it's, I mean, what I tried to say is that this...
Is it a sign or unsigned quantity? It's VADM. Does it have a sign or not in your convention?
No, because I can compare in any place.
So you have no sign. It's only the modulus.
Mm-hmm.
And then how do you know that it is shifting? Is there no sign here?
No, because in fact here he identified what another works have recorded. Because to know that the polarity happened, the reversal of polarity happened, we need to do direction. We need to obtain directional data, not intensity data only.
That's right.
But we can associate this decrease in intensity with these events of excursions and reversals. I only put it here to show that these sediment cores are useful in this way, and are useful because we can see the behavior of magnetic field in a continuous way, different from, for example, volcanic rocks that are punctual records. But it's useful as well because in this figure the authors used the volcanic records to calibrate this part of curve.
Axiom means always referred to the rotation axis of the Earth. So if in the case of excursion, the axis is in the equatorial plane, then we have a zero here.
Axial is only to say that is symmetric, not that is aligned with the Earth rotation.
Not aligned with it.
Not aligned. It is tilted.
Yeah.
Only to say that it's symmetric.
So the reversal is in this picture visible at this peak where you have written Brunis Matuyama, which it's going almost to zero. And this is indicating the reversal.
Yeah, and another indication is that going back to the time, the mean of the intensity changed, and okay, it increased again, but the directional data, it wasn't the same. So the intensity data is not enough to know that the reversal occurred.
But we have the directional data.
You have it actually on the right.
On the right.
Yes. And at 0.8, you do see that above 0.8 it was all black. Yes. Yes. That's 0.8 where the last reversal is. Yes.
In principle, anytime you have a zero, is reversal.
Sorry?
Anytime you have a zero, I'm sorry,
no, not zero. What we use to confirm is that when the directional change, the direction changed and don't back to the original pole, it is a reversal. Because sometimes the intensity can be really low, but it's back in a short period of time. And when it is maintained during million years, so we know that it's a reversal. Here, maybe 1,000, 2,000 years, it was like this intensity and back, and the inclination was tilted and back during a short period of time. I don't know if it was clear.
In the second panel, what are you showing there? You see
Here?
it says reversal frequency, yes.
Yeah, I showed that it's difficult to know an average for this frequency. With some works calculated that this frequency for 20 million years can be 300,000. But it's not true in all record, because here we can see that the frequency is not so high, and here it's even worse. There is no frequency. We don't know why this reversal happened, and why it happened in this period. I don't know.
So you know neither why it happened or why it doesn't happen.
Yeah.
But is that something like a wavelet analysis? What is called here? Do you know? I mean, because you do show frequency versus time, so that suggests that you have a wavelet analysis, which means you at different times you are.
No, maybe not.
No? What is it then?
I mean, there is a similar plot in that paper of Grasiane and Roberts.
Yeah. Do you know what this means then?
It's just say, I mean, you just take a gap and say number of reversal within this time, and it's a number of reversal per year. Actually, it's
Okay.
Then you should not have sharp boundaries. Otherwise, the curve will never be smooth.
Yeah, but you can have a running mean. I mean,
there's actually a similar. There's a plot like this in.
Sharp boundaries.
yeah, but then you move your spindle gradually.
You move, and whenever you make next reversal,
Oh, that's right. Yeah, there should be another jump. Yes.
Probably it is not.
But maybe maybe there are jumps. This is the plot in Grasiane and Roberts, the RMP paper, which is very similar to this.
Okay, good. Yes, yes.
Just to clarify your interesting figure here, these spectral-like things in the bottom and to the right, are they indicating which periods have been covered and which periods have not been covered by observations? You see, what does black and white mean in these?
The same like here.
It's polarity.
The black is a convention. The black represents the normal polarity, like today, north magnetic field and north geographic, and the white represents the reversal.
It looks more like something you find as a label in a supermarket.
Yeah.
Black and white
Barcode, yeah.
refers to the rotation axis. But is there also a panel not?
Sorry?
Black and white refers to the rotation axis. North and south is defined by the rotation axis.
the rotation of polarity of magnetic field with relation to the rotation of the axis Earth rotation.
What it is not so is your axis symmetric dipole moment. I understood. It is related to the magnetic axis. You define for each time magnetic axis, that I understood correctly. And then the picture gives the intensity of the dipole field related to this axis, which doesn't coincide with the rotation axis of the Earth.
No, it doesn't. I think it's true what you say.
So?
I think it is so, like you said. This is referring to the proper magnetic axis, this intensity. So it indicates that during a reversal, the dipole is not only flipping, it's reducing strength at the same time.
Yeah, what is reduced is the dipole strength. And the non-dipolar components get strong.
It gets strong.
Yeah, strong.
But it's interesting to note from these kind of black and white strip diagrams that even if you disregard from this long period with a constant situation, you have a very non-random behavior.
Yeah,
time
here
series
is
analysis
quite different, for example.
Yes.
You said random.
No, I said non-random in the sense that you have a high frequency of rather broad strips, and then you have places lots of
I see, yes, that's true.
thin strips.
Yes.
How reliable are these data? In order to determine the dipole axis at a given time, you need for this time magnetic measurements or magnetic data at several points on the Earth's surface, and they are available.
No, in fact, with 1 point sampling, we can see a reversion, but it's necessary to be lucky because it's difficult, and because continents move. In the past, continents was in another parts, so we need to get this direction and do the reconstruction to know where that continent was in the past, and to know that direction, that point. But it's enough in one sampling in one place.
It's like that in the ocean, for example, in the reach.
Yeah, there are another way to. I have a slide. Can I show it? No, it's because one easy way to see that these reversals happen is the spreading of ocean floor. So the region of magma is generated. There are standard. There are spreads parallel to the axis. So how much more far from the axis, older is this rock. I know the age, and I can see these reversals parallel. This is the best record that we have that show these reversals in the past. But we can see it only until 108 million ago. That is the oldest ocean floor that we have nowadays.
Where is it?
In the Pacific.
The oldest floor? Where is it?
In Pacific.
Pacific.
Pacific Ocean. It's the oldest ocean that we have.
So we have now like 800 years the same polarity.
Yeah.
And but when you look at it, it's like quite much longer than the other one. So we will reverse soon.
There are some researchers that think that we are next to a reversal because the intensity of the magnetic field is falling in the reports. So, before to show you how rocks get magnetized, I will briefly to say some basic concepts that are involved with rock magnetism. So it's important to know that inside the rock, the magnetic minerals have different sizes. These are the sizes: single domain, multi-domain, and pseudo-single domain. In this figure, we have an example of SD particle. Inside this particle, we have only one magnetic moment that is aligned in the direction of magnetic field. And when we increase the size of this grain, the trend is to increase the number of domains, like we can see here. So when it happens, the stability of the grain decreases. So for polymagnetic studies, it's necessary that the magnetic grain has this size, SD grain, because this kind of grain has high corrosivity. Corrosivity is a property that shows the capability of the grain not in acquire magnetization, but in keep this magnetization during the time. So in this graph, we can see that when we reduce this volume, we increase this corrosive force. So when this happens, we can keep the magnetization inside the magnetic grain during million years and sometimes billion years. So this is very important to be sure that the magnetization of the rock or sediment is representing the magnetic field in the past. Some question?
Okay, so what is the size of the domain? When you say, for example, in this graph, in the left, lower left, you say, for example, you have 20
the size of SD grain
yes.
is until 10 micrometers. It's really small.
You mean the size of the domain is comparable to the size of the grain?
The size when the grain is stable, the SD size, is until 10 micrometers. After that, the grain starts to divide and to create another domain.
10 micrometer.
10 micrometer, yes.
So that's comparable or even smaller than the size of the grain then? Yeah, it's smaller.
That is the size of the grain. If the grain is up to this size, it will have a single domain. If it starts to divide, it will have several domains. Right?
But,
this
it can't be, because then the line would be linear.
Sorry?
Then the line would be linear, because
It was not so.
the line is a line. You see the line, it's not linear.
So why need it to be linear?
Because the number of domains, if each domain has one polarity, and you plot the sizes, the grain size, which is actually rather huge, 300 micrometers for a grain. So that's very big for a grain, no? 300 micro.
it's big.
Yes.
In fact, we don't find this size of magnetic grains magnetized
Yes,
inside
right.
the rocks.
Not about 50. But
But there's a data point in 300. Is there a data point?
Yeah, but it is a multi-domain grain, and it doesn't get magnetized, or it gets, but it will lost fastly because it's energy competition. When I have some kinds of form of grains, I have a big energy inside this grain that will generate this magnetic field. And when I start to define these domains, I will lose it, and the magnetization will not be kept inside the grain.
So the message is that we should look for small grains. So the message is that if we want to know what the magnetization was long time back, we should look at the magnetization of small grains.
Yeah.
Or
Small magnet.
rocks with, or sediments with small grains.
But in fact, the rocks has big grains as well. But we use some techniques to separate the contribution of SD grain and MD grain.
So we could really trust single domain grains.
What are the grains in the basalts of the oceanic floor?
There are SD and MD, but most of them are small because the time to cooling is quickly. So in rocks that get cool quickly, the size of grains are smaller.
But I'm asking because basalt has an amorphous structure like a glass. So how can we speak about the grain then?
No, but there are grains. There are these grass, but there are SD grains as well, because there are different times to cooling in many parts of this basalt.
This analogy with glass is probably not correct.
It's not totally.
Because glass, of course, is really liquid, so it's really moving on long-term scales.
Yeah, in the sense of amorphous, but the basalt is not crystalline.
But the rock is really not, it's really remained rigid even over these long-term scales.
Sorry?
Does the rock really remain rigid?
No, but the rocks will also move.
They're all liquids.
Also liquid?
The metal is.
This is from Bible, right?
What?
This is from Bible, right? But the statement in Bible is
Maybe, but
from when the Deborah number comes.
but if the rock really, I mean, if the entire rock becomes distorted, of course, then the analysis will not work.
But the small grains will not.
Okay,
Right?
It's asking how if the rock is liquid at some time, then the analysis is not good. But,
okay, I will.
Not rigid, not liquid, but rigid. Is the rock rigid, sufficiently rigid over millions of years, hundreds of millions of years? I guess the answer must be yes.
No, but actually the continents move over these time scales, right?
It moves, yes.
yeah, but the
So
rocks
they
are
can also
still.
rotate.
But if it systematically rotates, then of course, all bets are off. Clearly. You agree, right?
Yes, so we need to know the history of the continents also, how they move.
No, let's talk about the sediment and whether that is sufficiently rigid. And I think the answer is yes, it is sufficiently rigid. It doesn't all of a sudden change by 180 degrees.
It's a matter of time scale.
Yeah, I'm asking about 100 million years. Yes, of course. I think the answer is yes. It remains rigid.
I not understand what you're talking about. Sorry.
No, maybe it doesn't matter even.
The English is
As long
difficult
as
for
I can
me.
send it correctly.
Why don't you continue with it?
Okay, I will try to make clear how rocks get magnetized. So
This is the answer.
this is the volcanic rock that you were talking about. What happens is that when this rock is melt, the magnetic minerals inside this rock don't have any orientation because the temperature is too high and the magnetic moment inside these grains will not align the direction of magnetic field. But when I decrease this temperature, the energy inside the grain starts to be higher. So the strength of Earth's magnetic field is able to align these grains, these acid grains. I mean, it aligns another grains as well, but the other grains will not be able to keep this magnetization during million years. But I didn't understand the doubt that you just.
No, I was not doubting it. I think Google
No,
was
I
doubting
agree.
it. The other said is the rock is like a glass and it can be distorted, which I don't think is true.
Ah, okay. Well, you mean when about metamorphic rocks?
No, I know it is.
Okay.
If I
I
get
have
your
seen,
point, sometimes rock can melt during the period of time
Even if it's not
from
melting.
the recent generation until now. And these metamorphic rocks are not useful for magnetism. water. But the basalt that's generated in the ocean floor, it doesn't happen. Metamorphic process. In the surface, no.
So unless it's not subducted, it is useful. No?
Yeah.
Once it is subducted, it starts to be normal.
It's not useful anymore. So this kind of magnetization, that is an equilibrium between thermal energy and the magnetic moment energy inside the grain, is called the thermal remanent magnetization, and it happens with igneous and volcanic rocks and ceramics, archaeological ceramics. Ceramics during the burning of inside the ovens. But in sediments that are the samples that I used in my work, there's a different kind of magnetization. So, first of all, it's necessary that the sequence of sediments be collected in an environment where the deposition was, the process of deposition was water. So here there are some magnetic particles in deposition in a water column, and the alignment of these particles will be governed by this equation, where the first term is the inertial term that we need to disconsider, because we assume that the acceleration of particle is zero. The other term is the viscous alignment, and it changes based on the size of the grain and the viscosity of the liquid. And the last term is the magnetic force, where the μ0 is the magnetic permeability, the size, m is the magnetization, h is the applied field, and theta is the alignment between the magnetization and the field. So the equilibrium between these forces changes according to the grain size. So how we can see here, multi-domain grains that are big cannot be aligned by these forces, because they will be aligned by mechanical force. So if I have an environment where I have high energy, for example with strings, these grains will get oriented by this force. So once more, I say that it's necessary that the size be in this range, single domain range. So here, the magnetic force will be able to align these magnetic grains. The name of the magnetization is detrital remanent magnetization. But there are another magnetization that's called the post-depositional remanent magnetization that happens when this grain crosses the interface between water and sediment. And when this grain is in this zone, the G zone, before the consolidation of the sediments. When the grain reaches this region, it can be affected also by mechanical effects like activity of biological activity. And so the magnetization that was acquired in the water column can be lost, and only the grain keep the new one. But another problem in this magnetization is that during the diagenesis, when the sediments are consolidated, it will lose water and space, so maybe even this magnetization can be lost.
So the quantity eta in this middle term is the one which then increases as the rock cools? Correct? The next one is which is left.
This kind of...
Eta term. I mean, when the rock now cools, right?
No, in fact, this equation doesn't apply to rock, igneous and volcanic rocks. It's a different kind of magnetization.
This is for sediments.
This is only for sediments and sedimentary rocks. It's we need to see that grains are depositing, and the magnetic field applied will align this grain. But inside the rock, the equilibrium is not based on this equation. It's based on the temperature and the coercivity of the grain. So when I start to decrease the temperature, the grain gets magnetized in the direction of the magnetic field that was applied in the rock during its generation. It's a different kind of magnetization.
Okay. So the viscosity is constant essentially for inductive purposes.
Yeah, you can give us some kind of viscosity.
This is the viscosity of the medium.
Yes.
It's the liquid viscosity.
But the equation is valid in the water and maybe in this benthic layer too, is it?
In fact, this equation is not used here because here there's no the particle is not depositing, is not falling. The particle is above the sediment, but there are some small spaces. There are porosity. So inside these spaces, the grain can get another alignment. And so in my work, I used a 2-meter long core that covers only this last 6,000 years. I subsampled these cores with samples at the middle of the core to avoid the shear effects that can happen in the edge during the sampling. And then I put these samples in equipment like this. This is a magnetometer cryogenic that will measure the declination, inclination, and intensity of the magnetic field. This sample is another one. We can perform measurements in discrete samples and in continuous samples.
Make us the samples.
I will show it now.
The same question.
Okay. Before I show it, I will only say one important problem that we have in studying magnetic field. That's the fact that there are a scarcity of data in the south hemisphere. This figure is showing archaeomagnetic and sedimentary records of magnetic field that are used nowadays to construct some models. And how these models are based on the existing data, so maybe it doesn't represent in a good way the magnetic field in regions where we don't have data.
What's the difference between light and dark?
Then dark is there are more data. And when we observe this other figure, it's even worse. These are only the sedimentary records that we have around the world. So this model that was performed for representing magnetic field here probably is not representing in a good way because, like I showed you, there are an anomaly, magnetic anomaly in this region. So probably there are some local variation here. So this was one of the motivations in my work that I chose my place to sample here. And in my PhD, I will analyze another 5 cores collected here and here. This is the region I will show.
So these are young oceanic sediments. Yeah.
Not only young.
Not only.
Here, for example, there are sequences that reach 8,000 years.
But I mean the samples you
Yeah. Only 6,000 years. In fact, I tried to recover from 11,000 years, but the sediment was movemented. I don't know. Some mechanic motions happened during the sampling. This is the region where I collected my core in southeast Brazil continental shelf, and this region is affected by this Brazil current southward and this smaller current that is originated in Rio de la Plata and brings low salinity and temperature waters to this latitude. It's important to mention about hydrodynamics in this region because the magnetic mineralogy that I performed made with the analysis of magnetic mineralogy, I could to do a paleoceanographic model for the last 6,000 years in this region. So I could infer about source of sediments. I will show you. But first, briefly, to recover the relative paleointensity data, we need to assume that the relationship between magnetization and the magnetic field is a linear relationship. So to do that, we need to normalize the natural magnetization of the sediment using some parameters that we take in laboratory. Because throughout the sequence, the sedimentary sequence, there are changes in the size of the magnetic minerals, concentration of magnetic minerals. So the intensity of magnetic field, the change in intense magnetic field, not only is due this Earth magnetic field, but due these changes. And when I use these parameters to normalize my record, so I can remove these effects. I was actually.
One thing I missed now, because all the analysis you were normally doing in these zones where new basalt emerges in the previous transparency.
No, I didn't. Your question is.
I mean, when we were talking about this Pacific thing.
No, yeah, it's because
basalt emerging, and that of course lines, there the magnetization lines up with the overall magnetic field. But now you're talking about locations where you don't have emergence of new basalt.
No, it's not that we don't have new basalts. We have new basalts here.
Oh, I see.
But we don't have paleomagnetic data.
Yeah, I see. Oh, sorry, I see that.
And here we have, sediment is the best record for recover magnetic data because it exists in our world.
Exactly.
But we don't have this magnetic data.
Yes.
I'm sorry, I was not clear.
And then the oldest sediment that you said is only 11,000 years old, or are them older ones?
In my work, the oldest one is 6,000 years.
Yes, right.
I tried to recover one oldest, but it was not possible.
In other locations in the world?
There are, yeah.
And how
That
old
yellow curve that I have showed recorded the date, the last 800,000 years
Yes.
using marine cars.
800,000 years, yes. So exactly during and there was no reversal.
There is.
800,000.
Yeah, it's really big because it's in the abyssal places, really deep parts of the ocean.
It's 1,000 times shorter than the time of the last reversal.
My record?
No, in these 800,000 years, there was no reversal, which was the first.
Only the last one.
It's million years ago.
Yeah, that's right. That's why it's 1,000 times longer.
8,000.
8,000 millions?
800,000.
800,000.
800,000, that was the first. I'm sorry. No, that's only 10 minutes.
Sorry for the questions.
No, don't worry. I'm sorry because I'm not so clear. So, okay, I can't, it's not necessary to go deep in these techniques, but if you want, I can explain it after. So, first I will show you the paleoceanographic model that I made using the environmental magnetism analysis. So, this parameter is the susceptibility, and we see a decrease, and after this smooth increase and a significant increase in the top. That shows us that in this part of the record we have a big input of ferromagnetic material. This other parameter is a relationship between a parameter that represents single domain grains and a parameter that represents multi-domain grains. So when I do this relationship and I have a decrease, like here, I can say that it's increasing the input of multi-domain grains in this record. So this parameter is useful to analyze the size of the grain into the record. And this other parameter is useful to analyze types of mineral, specifically magnetite and hematite. So when I have a decrease in this S ratio, how we see here, we can say that the input of hematite in the record is increasing. And hematite is a kind of mineral that most of the time comes from continental sediments. So using this, our magnetic data associated with paleoclimatic models that exist for this region, we divided this last 6,000 years in 3 periods of sedimentation. So the first one, when the sedimentation, the sediments were mainly from Argentine continental shelf. We know that because these parameters show smaller grains in this part, and there are some works that have been published in Argentinian soil that shows that the sediment that arrive in the continental shelf of Argentina are small grains, like this one that we have found here. In the period 2, we had a mix between the Argentine continental shelf and the La Plata River. It happens because some models show that 6,000 years ago, the level of the sea was really high in comparison with today. So it flooded the La Plata River, so the continental contribution couldn't reach the continental shelf of the Brazilian continental shelf. And when, from 6,000 years until now, the tendency of the sea was to decrease. So I started to have the contribution of the La Plata River. So here, a mix. And in our record, it was proved by the hematite presence. And this suddenly increase and decrease in these parts and in these parameters show that besides this decrease in sea level, it is associated with wet conditions that started to domain in this region. Because if I have more rain, I have more contribution from river to the continental shelf. So now about the magnetic field, I'm almost there, okay? This is a stereogram that we use to represent the inclination and declination of magnetic field. Here we need to look at this sphere from the top. Like here is like the Earth. So here we have the zero inclination, and when we look from the top, this zero inclination is over here. So inclinations that are in this position are 0 and increase until 90 degrees. Open circle positive and closed circle negative. And the declination is represented from north clockwise until from 0 to 360 degrees. The mean direction that I found for inclination was minus 23 degrees, and it doesn't fit with the expected inclination of field in this region. But to test if this could be because of the diagenesis process that may cause a loss of the direction, we used a program that tried to make the inclination back to the original inclination. So we found minus 30 degree inclination, mean the inclination, that has still a difference from the expected, but so what we think is that this main direction probably is representing local variations of magnetic field. Because we know that in this South Atlantic region we have the magnetic anomaly, and these models only consider the dipolar component. And the declination, how during the sampling process we don't consider the north magnetic, so any place inside this circle could be my declination. Okay? And about intensity, these are the curves that I obtained using these parameters to normalize. And I compared my curves with the models for the regions and with the data that exists in South Argentina, data from lakes. And here we can see that the variability of my curves are bigger than in the model curves. More if we compare with this pink curve that is a model that is done only considering the dipolar component. So maybe these variations is representing again the non-dipolar components. But we can see a general trend from 6,000 years until 4,000 years that is presenting my data in the models and in this data of lake. And in this part of the data, we can see a trend again that is decreasing the intensity of magnetic field from 1,500 years until 1,000 years. That was that was calculated in the same way by the models and recovered from the Argentinian sediments. So this is my work. I know that we have a lot to do to generate more data in South America. And if you want to ask something, I'm sorry. I know that I am really confused with my English.
That's great.
I wondered about these variations we saw with characteristic times of couple of hundred years or so, after two intensity variations. Are they significant or could they be going to equally?
I didn't understand. Sorry, I'm not so good with English.
If you show the last, can you show the next to last slide? Yes, that one.
That one?
No,
okay.
no, that one. If you look at your curves there, you see variations by about a factor of 2 within a few hundred years. And my question is, are those significant or could they be due to measurements?
Yeah, in fact, it could be due to measurements. This is the reason because we want to publish still this data, because any journal will accept a data only from one core, one sample. We need to compare our data with another samples in the same region, but it doesn't exist. So maybe it's because non-dipolar variation, and maybe it's because measurements are a process of sampling. I'm not sure.
So the units on this last plot are what?
It's microTesla, but I didn't put because it's normalized. The curves are normalized because I used different parameters.
Yeah, I see.
So the values are different.
On the previous transparency, we had these polar diagrams. So this showed mostly azimuthal angle and the inclination, yeah? But there were no numbers.
So the inclination is represented from 0 at the edge until 90 degrees.
Oh, yes, yes.
So here, the mean was 23 degrees, but there are some values from near 0, like 3, 5 degrees, and other values.
Right. And then this is south, yeah? Or pointing towards...
Yeah, the declination we can't know because it was not oriented with relation to the north magnetic. So my declinations can be around the circles, in any place. But if we have, because if we have another record to compare, so we will know that the declination are here, or here, or here.
Yeah.
But we can't do that. So we will keep it here until to have another data to compare.
But still you have put the points at different declinations. Why?
Yeah, I don't know.
But I still don't understand why that's not possible. If you can
Yeah,
measure the
because it's
inclination.
not in the north pole.
What?
Because it's not in the north pole. If it happened, it could represent a reversal of polarity, but it didn't happen the last 6,000 years ago. So probably it is doing errors.
But the inclination has to do with the inclination of the field within the rock, right? So how come you can calculate the inclination but not the declination? But it's the same.
Because declination is with relation to the geographic north.
Yeah.
So if I'm collecting my car in an arbitrary way,
I see.
so I can't know.
Yes, of course.
This cannot be avoided by the preparation technique.
Yeah, now we have some equipment that permit you orientate with the sample, but the fact is, in my institute we don't have this equipment, and the cars were a gift for me. And
So it has been rotated during the process.
yeah.
What resources are required to take a core like this?
Sorry?
What sort of resources are required to get a core like this?
How much money you need to
a
have
lot of. This is the reason because I cannot do that, because I am in Geophysics Institute. No one there wants to study sediment. I am the only one. So this car was a gift from the Oceanography Institute, but they don't do this kind of analysis there. So it doesn't matter if the orientation of the car is north, south.
But sorry, I mean, when you say the orientation is not named, so we can't determine the inclination, then still you know the relative orientation of all your samples along the core all the time. So these dots are collected anyhow, but they may be anywhere together around the circle.
Together.
Great.
Okay, so then the angle actually has a
The
meaning.
angle actually makes sense.
Yes.
It does have a meaning because it's relative to the same core.
Yeah.
But there's an overall normalization.
The sign of this inclination.
Offset question.
Yeah, because
Yeah.
it's not near the poles, and it doesn't have
Yeah.
a reversal. So probably this is but the declination.
And you look at the absolute values of the magnetic field. Do you see that this is like lower than measured in like Europe or
Absolute values in microtesla, for example, you mean?
yeah.
So using sediments for recover the magnetic field, it's not possible. We use this is the reason because we call relative paleointensity. The absolute paleointensity, how we call is the name, we can only obtain from rocks and ceramic because we can. A gente pode fazer temperatura no laboratório.
You can induce temperature variations and then.
Simular a situação durante a geração. We can simulate increase in the temperature, how it happened during the generation of the rock. So doing that, we can pick up a coefficient that will give us the exactly value of the intensity.
And you can
using sediment, it's not possible.
But you can do experiments of sediments in water, for example.
Using temperatures.
No. For have an absolute value of the magnetic field, to compute a coefficient like you do in ceramics, but doing experiments of sedimentation.
Okay. Do you use in models?
No. I mean, in sediments you know that the grains are falling down, but you can do experiments of this or not.
Okay. There are some experiments that have been done, but it wasn't successful. Because it's difficult to represent the environment when the sediments are deposited.
So with your technique, you can observe the unknown in the that you have there very good magnetic field.
If I can see that in my
Yeah,
record,
you can see.
yeah, in my hypothesis was these two. One, that this can represent the local variation, the anomaly, magnetic variation, or errors. I don't know, but it's possible to record this anomaly. That data that I showed from the other guy in my group probably is showing this anomaly because it doesn't fit with the models for the region.
How long was the core? And yeah, how long?
2 meters.
2 meters.
Yeah.
Yeah, sorry, but then how deep was it? I thought it was.
The water column, like 100. It was on
100
the continental shelf. It's not possible to see, but
100 meter
it's a lot.
deep, and then in the 100 meter depth you had this 2 meter piece of core.
Yeah.
And 2 meters means 6,000 years.
In this case, yeah, but it can change. For example, this other car that I will analyze during my PhD, that was collected here, I have 7 centimeters of sediment, and only the last 700 years. So the sedimentation rate is really high. This is a really good car. Maybe I will get some important features of magnetic field with this car, because it's good when sedimentation rate is high because we can see the features. If the sedimentation rate is low, we can smooth some quickly changes of the magnetic field.
It's because the mountains are close. That's what it's
Probably, yeah.
No more questions? So thanks Grasiane again.
Thank you.